No. Okay, so thanks for the invitation. Very happy to be here. So today I'm going to introduce you a little bit what we are working on analytics for IoT. So I would like to present some open source software that we are working on, and then some methods, some algorithms that we use in this open source frameworks. So first, I would like to start. I will start motivating the Internet of Things setting. So I'm going to try to convince you that this is going to be something really, really hot in the next 5 years. So there's a lot of things going on, and I hope that you see that this is going to be important. So let me start with first introducing the settings. So the Internet of Things is this set of objects that are connected through the internet. So the predictions are that we're going to have a really, really huge number of devices connected through the internet. So Gartner, for example, is predicting that in 2020 we're going to have around 20 billion devices, and IDC is projecting that we're going to have around 30 billion devices. So this is a lot of devices, and if we look at the quantity of data that is going to be produced on real time and we would like to analyze, this is going to be really, really huge. Okay, so there are many, many applications on the Internet of Things. So we can start, for example, mentioning the ones on energy management. So, for example, EDF in France wants to have one smart meter in each one of the houses. And then they are not only interested in aggregating this information, they are also interested in disaggregating this information. So this is going to give, if they are not, these smart meters, if they are not connected, they're going to give one data every 10 seconds, but the ones that are connected through the internet, they're going to give continuous data. So it's going to be a lot of data. And as I say, there are two possible things to do. One is to aggregate this in terms of cities, but also the other is disaggregate. So we have the total number of the consumption, and then we would like to know what is the exact consumption for each one of the one of the things that we have in the house. No? The washing machines, heater, all of these different things. There are applications also now in smart homes, so you know all of these devices from Amazon, Google. This is going also to have a lot of data, and we'll have to analyze this. Smart cities, this is also an application that has been there for many years. So the idea here is that we want to optimize what is happening inside the city. So we have these examples of, for example, to optimize the traffic, the parking slots. So we have all of this set of sensors and actuators that are going to be really, really useful to know what is happening and then make better decisions. And also, for example, we have on the lights, we can decide when they can turn off or on, depending if there are people around or not. Okay, and then finally, we have also applications in industry. So this is also something that is going to be really huge in the sense that there's a lot of interest in trying to have these nearly automated factories where we have all the data of what is happening there, and then they can be run nearly in an autonomous way. So if we look at the applications that the companies are spending the money, so we see that many, many projects are around this connected industry, but we have also applications on smart cities, smart energy, this autonomous car right now that is becoming very popular, smart agriculture, but also connected buildings, health, smart retails, and smart supply chain. So you see there are many, many different applications, and this is something that is growing. As I said, industry is something that's going to be very, very important for IoT. So we have this idea of Industry 4.0 that comes from the German government. So the idea here is that we had 4 industrial revolutions. So the first one was the revolution based on steam. The second one was the one based on electricity. The third one was the one based on computers. And finally, this fourth one is the one that is based on these computers connected through the Internet of Things. So the idea in this Industry 4.0 is that we would like to have a virtual copy of what is happening inside the factory. So we like to have all the data. So then many decisions will be automated, but also the ones that still they have to be decided by humans. This is going to be much easier if we have really all the data of what is happening there. And only to show you how this is, Internet of Things is something that is growing, let me show you this graph. So this is from the EMC Digital Universe study. So if we look at the percentage of data, of all the data in the world, this digital universe data, that comes from Internet of Things, if in 2013 was only 2%, now in 2020 it's going to be around 11%. So it's still growing. And also, if we look at the popularity of the term in looking at Google Trends, so if we compare the Internet of Things with big data, we see that big data was something really popular around 2013, 14. But what we see that recently, the Internet of Things is becoming much more popular than big data. So yeah, this is why we think that really Internet of Things is going to be really something important in the next 5 years. And as you know, there's going to be a lot of time series data and a lot of streaming data. Okay, so in terms of analytics, the difference between the Internet of Things and the static, the byte setting, the traditional setting, is that in the traditional setting, when we do traditional machine learning as classification, regression, what we do is that first we have all the data set in memory or in disk, and then what we do is that we build our model. And then usually we don't have constraints on time and space, so usually we have the data set and then we build our model. And also we suppose that there is no change on the data. So we suppose that all the instances that we have inside the data set are going to correspond to the same distribution of the data. Okay, so this is the standard setting. But yes, as we know in the Internet of Things or in the streaming setting, what is happening is that data is arriving continuously, and usually we cannot store all the data in memory or in disk and then do the machine learning process. So here what we are interested is that we want to update our model. So instead of waiting to have all the data and then build our model, what we are going to do is that we are going to update our model continuously. So that's the difference. So we have our stream is arriving, and then every time a new example arrives, what we do is that we update our model. So the advantages of this is that first, we don't need to store all the data in memory. So we see the data, we update our model, and that's all. We don't need to store it. So that means that we are going to be much more efficient in terms of time and memory. And the other important thing is that data may be changing. So we don't need to suppose that data is going to be static. As in many real situations, the distribution of the data is going to be changing. Doing this update of the data, we have the advantage that then our model can be updated on real time and can correspond to the recent distribution of the data. So this is what we call this data stream approach of doing machine learning, doing classification and regression. Okay, so let me show you an example of this, so why this is important. So this is an example of data from spam from Yahoo News comments. So the idea is that if we have our model, it's the blue one, and we train it at the beginning and then we don't update it anymore, what we see is that over time, the performance is going to be going down. Instead, if what we do is that we have this online model that we update continuously, what we see is that the performance is still good, so it doesn't, the performance doesn't decrease. So this is why updating the model, it's really a useful solution, and it helps us to have accurate models. Okay, so this is what we call this data stream mining setting, IoT stream mining setting, where what we have is that we do only one pass over the data. We don't store the data. We have to be very efficient in terms of time and memory. And we need to be able to adapt to the changes. So we need to detect changes on the stream and then update our models corresponding to these changes. So sometimes, having the exact solution, especially when we are dealing with this large quantity of data, is going to be really expensive in terms of time. So then in streaming, we'll be happy with an approximate solution. So this is the case. Imagine that to have the exact solution, we need to days to compute it. If we can have an approximate solution that we can compute it in seconds, we'll be happy with this. So this is why we use these approximation algorithms, that we have solutions with a small error epsilon with high probability 1 minus delta. So let me show you an example. So imagine that we want to have a stream of events and we want to count the number of events. So imagine that we have only 8 bits. We have only one register with 8 bits. So how many events we can count? So as we are using 8 bits, so we want to count the exact number, it's going to be only 256. But the nice thing of streaming is that we have this, this was the first paper on streaming. So it's called Counting Large Number of Events in the Small Registers by Bob Morris. So he was able to, using an approximate method, he was able to store 130,000 events using only 8 bits. So how he was able to do that? So how he was able to store 130,000 events into 8 bits? So the idea is that instead of storing the linear number, the count, he was storing the logarithmic of the number. Okay, so that's the idea. So the idea is that instead of storing the exact count, he was storing the logarithmic. The problem, as you see, is that it's really different, these two functions. So it could be nice that at least from 0 to 10, we have the same behavior. So yeah, if we change these factors inside the logarithmic function, we have from 0 to 10, we have a similar behavior. So the counter is going to, from 0 to 10, is going to work very, very similar. And then after 10, yeah, performance is going to be different. So how this works? So the method is very simple. So in if we compute the exact solution, what we do is that for each one of the events in the stream, what we do is that we add 1 for each one of the events. So that's we have the exact solution. In that case, with the approximate, the only thing that we need to do is that for each one of the events, we need to take one random number between 0 and 1. And then if this random number is less than this threshold, then we add 1. And if not, we don't add it. Okay? Doing this, we can have this approximate solution and this approximate guarantees. Then to store the logarithmic, the only thing that we need to do is that this p should be a power of 2. So if we do this, then we can store the logarithmic, and we have this very nice approximate method. Okay, another nice approximate method that is very used in streaming is what is called this streaming sliding window. So the idea is that if we want to compute the average and the variance of a stream, usually this is easy. If we store from the beginning, we only using counters. We only, for example, to compute the average, we only need to compute the sum of the numbers and the number of events. So we only having 2 counters, it's enough. And also for the variance, it's similar. The problem is that what happens with a sliding window. In a sliding window, every time we add a new number, we need to remove the oldest one. So in that case, we cannot do only using 1 or 2 counters. So there is this nice work of Datargianis, Indik, and Mawani that they show how to do that, how we can use a logarithmic memory to store a streaming sliding window. So this is a very nice result. Of course, we're going to have an error, but this is going us to allow to have a very nice approximate method. The idea then is that instead of storing all the sliding window, what we store a number of a logarithmic number of buckets. So we divide the sliding window into buckets, and then we need only to have a logarithmic number of buckets, and then we can compute all of these statistics in a very, very efficient way. Okay, so yeah, let me start. Let me move to the open source software. I'm going to talk about MOA. So MOA is this open source software specific for data stream mining. It's from the Weka machine learning group at the University of Waikato in New Zealand. So the idea is that in Weka, usually you need to have all the data set, store it in memory, and then you can build your model. In MOA, everything is streaming, so we need to update continuously our model. So we have the stream of data that is arriving, and then we don't store the data. What we do is that we update it continuously. So it has many different methods, as classification, regression, clustering, frequent pattern mining, and it's very easy to use and very easy to extend. So, well, I suppose that you know Weka. Weka is a very popular software for doing machine learning. So Weka is really the name of a bird in New Zealand. New Zealand is famous for having birds, native birds that are only in New Zealand. So Weka is a bird, but MOA is also a bird. The only thing is that MOA is extinct right now. But you see that it's really much bigger than a weka. If we compare the size of a moa with a weka, we see that the moa bird was really, really much bigger. Yeah, and this is comparing the size of the moa with a human. So it's really, really much, it was a really big bird. Okay, so as I said before, we have this stream setting that is really, really different from the bytes, because here we have data that is arriving, and we need to be very, very efficient in terms of memory and time, and we need to be able to adapt to the changes on the stream. So in terms of classification, the evaluation is going to be different, so we cannot use the classical bytes evaluation as cross-validation. So we have two different ways. One is holdout evaluation, and the other is interleaved test and untrained or sequential evaluation. Holdout, the idea is the same as in the byte setting, so we have different data for testing and for training. And in that sense, we have, like, instead of having two different data sets, we have different data streams, or we use different data for testing and streaming. Another method that is specific for data stream mining or for online learning is what is called this sequential evaluation. So here what we do is that we have this stream of data, and then every time a new instance arrives, first we test and then we train. Okay, so as we are first testing and then training, this new instance that we are using to test is an instance that we have not been using for training. So then it's fair. We are not doing anything wrong. And then after that, after we have tested, we can use it to update our model. So this is what is called this sequential evaluation, and it's the one that we are using in streaming. Okay, so MOA has this nice graphical interface. So we have all of these methods. So this is the graphical interface for clustering. So in this case, what we see is that we have all the clusters that the difference is that they are going to be evolving over time. So this is the main difference of the byte setting and the streaming, is that here we are not doing only a clustering of the points. Here the clusters are going to be moving. Clusters are going to disappear, appear, going to merge, split. So everything is going to be happen continuously. So we need to update our clusterings models continuously on time. We can use it also from the command line. So we can run these experiments using from the command line or from the Java API. Okay, just to mention some methods that are state-of-the-art in classification for streaming and we have in MOA. So yeah, let me show some examples on classification where the goal is to predict the label of the examples. So in regression, we'll look at the numeric values, but here we are going to look at the labels. So yeah, we have this very classic method that is Nightbase. So Nightbase is this method that is based on the Bayes theorem. And basically what we are doing is that we are computing the probability for each one of the classes. So given the example, we are looking at all the probabilities for each one of the classes, and then we choose the probability, the class with the highest probability. So we are supposing that the attributes are independent. So this is a big assumption of Nightbase. And the nice thing of this Nightbase method is that it's based on probabilities, and this probabilities is based on statistics that are stored in counts. So then it's very easy to update model. So every time we have a new instance and we want to update the model, we only need to update the counts. And then when we compute the probabilities, we are going to compute the probabilities that are based on these counts. So the nice thing of Nightbase is that it's already incremental. It's already streaming, so we don't need to do a streaming version of Nightbase because Nightbase is already incremental. A Perceptron. So the Perceptron is also a linear classifier that is basically contains this set of weights. And then, yeah, every time we see a new instance, every time a new instance arrives and we want to update the model, we are going to use a stochastic gradient descent in a way that we minimize the mean square error. And we do that for each one of the instances. Here, the difference between the streaming version and the bytes version is that in the bytes, we are able to do many, many iterations over the data. And in streaming, we do only one iteration. But the method is already incremental in the sense that we are updating our model one instance by one instance. Okay, the case of the decision tree is a bit different. So decision tree is a very nice method in the sense that it's really easy to interpret. So we can really understand what is going on. So it's not a black box as other methods. So here we can understand really what is happening. So we have all of these attributes that are we split by different attribute values. We have these different branches, and then so we can go through the tree to arrive to one leaf and then do the prediction. So the nice things of decision trees are first that are easy to interpret, and the second one is that we can use that in powerful methods based in ensembles of trees like a random forest or GVDT. So this is why these decision trees are really, really useful. The problem is that decision tree is not really streaming. It's not really incremental method. And the reason is because every time we need to decide if we split or not, we need to look at the statistics, at the data that we have in memory, compute the statistics, for example, if we are using information gain, compute the information gain for each one of the attributes, and then decide what is the best attribute to split. The problem to do this is that, we need to have data stored in memory. So that's the problem. So this is why there is was need for a streaming decision tree. So this is this halving tree that is from Pedro Domingos in 2000. The idea then is that what we are going to do is that instead of looking at the data that we have in memory, what we are going to do is that we are going to wait 2 new instances to arrive. Okay, so that's the idea. So we don't have the data stored in memory. So if we need to decide to split, the only way to have this information is to wait 2 new instances to arrive. Now, the point is, how many instances do we need? How many instances do we need to decide if we split or not? So this is why, to know this number of instances, we use the halving bound. This is why this tree is called halving tree. Okay, so, and then basically what we do is that when we want to decide if we split, what we do is that we look at the difference of the information gain of the 2 best attributes, and we look if it's higher than this threshold that has been computed using the halving bound. So doing this, we have guarantees that the tree that we are growing is going to be similar to the one on the byte setting. One of the nice things of the halving tree is that we have theoretical guarantees that if we have enough data, we are going to have a similar tree to the one used in the byte setting. Okay, so that was for classification. If we look at regression, where our goal is to predict numeric values, not labels, the things are similar. So we can use, for example, the perceptron. We are going to do exactly the same. We maintain this set of weights, and then we, using a stochastic gradient descent, we are updating it continuously, and then we use the gradient that is computed minimizing the mean square error. Okay, so in that sense, it's really similar. For decision trees, in that case, regression, the decision trees, it's very similar. So the only 2 changes that we need to do is, first, we cannot use information gain. So in that case, what we want to do is that we want to reduce the variance. So we want that the instances that are in the same leaf, they are really similar, so the variance should be small. So then instead of information gain, we use this variance reduction. And the other thing is that instead of, in the leaf, instead of predicting using the majority class that is present there, here we are going to look at the average of the value of the instances in the leaves. Okay, so that's the 2 differences that we need. Finally, we have another method that is based on rules. So the idea is similar to decision trees. Here, instead of having a tree with all the rules in this tree structure, here we are going to have a set of rules that we are going to have these conditions as we had in the decision tree, and then finally we have a prediction. So the way of this, how these rules works, we start with a default rule, and then from this default rule, we are going to start creating these new rules. We are also going to do that based on the halving bound. So we continue growing this set of rules, and then when we want to do a prediction, basically what we do is that we use the combination of all the that are inside this instance. So it's a very a very good method also to do regression, and similar to using trees. Okay, so yeah, let me mention now that usually data is not static, so data is going to be really changing, so we need to apply concept drift and detect the change and then update our models according to these changes on the data. So to do that, we have these algorithms that are called change detectors. The idea is that we want to detect concept drift. Basically, we have this data stream of values, and then we want to have two outputs. One is to raise an alarm when we detect change, and the other is that we want to have a prediction for the next instance, minimizing the error. So basically, what we have is this structure. We have this concept drift detector is going to have first an estimator that is going to estimate the next value. We have a change detector that is going to raise the alarm. And then we have the memory that is going to be storing some statistics that are going to be useful for improving our change detector method. So there are many different change detectors. So we have this QSUM, or cumulative sum. This is the very, very simple. So the only thing that we do is that we have the errors, and what we do is that we accumulate the sum of the errors. And when this sum is higher than a certain threshold, we raise the alarm. So this is very, very simple. The nice thing is that we use we use only counters, so the memory that we use is really small. The disadvantage is that we need to define this parameter. So we need to define what is this threshold. And that could be a problem in the sense that then you need an expert user to decide this threshold. Another method is this statistical process control. So this is based on the idea of Six Sigma. So here what we are doing is that we are supposing that we have the error is going to be following a Gaussian distribution, and then if the value that we're getting is out of this Six Sigma, so out of this 6 times the standard deviation, we are going to assume that this is a concept drift. So let me show you this example. So here we have the error rate of a stream classifier. So at the beginning, the error rate is high. After we get more instances, the error goes down until it gets into a stable phase. When we are in this stable phase, if nothing happens, if there is no change on the data, we are going to be inside this phase. But if there is change on the data, then the error is going to go up. And once the error goes up, first at 2 times the standard deviation, we are going to raise a warning signal, and at 3 times we are going to raise a drift signal. So the idea is that once we are in the warning, we can start growing a new classifier. And once we really detect the change at the drift level, then what we do is that we replace the old classifier by a new one. Okay, so this is how this method can be used to adapt the classifiers. And this can be done not only for the classifiers, but can also, for example, in decision trees, we can do that also for the branches inside the decision tree. Okay, so yeah, then this is these change detectors that we can apply to this classifier method. So we have this concept adaptive BFDT, that was the first decision tree that was adaptive. So in that case, what it's doing is that it's keeping a decision tree that is consistent with a sliding window. The problem here is that it's consistent with the sliding window, but we need to specify what's the size. So maybe, yeah, we decide that the size is 10,000 instances, but maybe the change is around 1 million instances. So it's very difficult to decide what is the correct size. No? So if the scale of change is seconds and the sliding window if it's hours, this is not going to work. So this is why there was this other method, this housing adaptive tree. So this is a method that is based on change detectors, in this case ADWIN, that is a sliding window change detector. So in that case, we don't need to specify the size of the sliding windows. This is going to be adaptive. So there's no need of deciding this. And then the tree is going to be, we have this change detector in each one of the nodes. And when there is change on the error, then a new branch is created. And if the new branch is better than the previous one, it's going to replace the previous one. So it's very simple, and the nice thing is that there is no need to decide any parameter because everything is done. So this method is based on this Adwin change detector. So Adwin is an adaptive size sliding window method. So the idea is that it keeps data from a sliding window, but it's, there is no need of parameters. So the idea that is adaptive means that if there is no change, the sliding window is going to grow, grow, grow. But if there is change, the sliding window is going to reduce only to keep the data that is consistent with the current distribution of the data. And the nice thing of this is that we really don't need to specify parameters. So this is Adwin. It has these properties of an optimal change detector. It's highly accurate. It's very fast detecting change. It has a low false positives and false negatives, and it has a low computational cost. And it has theoretical guarantees, and there's no need of parameters. This is really, really important because if you need parameters, then you need expert users to decide this. So the theoretical guarantees that Adwin has are on the false positive rate and on the false negative rate. And the nice thing of this is that as Adwin has these theoretical guarantees, we can also apply this to the machine learning classifiers that are using Adwin, for example, decision trees and the others. We have been applying Adwin to many, many machine learning methods. We applied it to classification, to Nightbase, to decision trees, to bugging, to stacking, to multi-label classification, to nearest neighbors, to random forest, but also in frequent pattern mining when we have streams of trees and graphs and we want to find the most frequent ones. So we have also been applying Adwin to these methods to be able to have these adaptive versions of the methods. Okay, and just to finish the method that we have in MOA, in terms of clustering, we have streaming clustering methods. This is really important in the sense that in streaming, data is arriving continuously, and we need to be really, really fast. As you know, for example, in k-means, usually we need to do this iteration. So we need to have this two-phase now to assign the points to the clusters and then to recompute the clusters, and we need to do that many, many times. But this is in streaming is really complicated because data is continuously arriving and we need to be really, really fast. So most of the methods in stream clustering works in two steps. So one is online, that is this idea of storing microclusters and computing that online very, very fast. And then after that, doing an offline phase where we apply the standard k-means or dbscan method. So imagine that we have a stream of 1 million points. So what we do is that we do online phase very, very fast. So we store 100 microclusters. And what we are doing is that we are updating this in a very, very efficient way, very fast. And once we need to compute the clusters, we run a k-means or a dbscan on these 100 points. So doing that on 100 points is really, really fast. Doing that in millions of points is going to be a problem. So this is how the clustering methods work, and they are based on this idea of microclusters. And then I think then is that we can keep that into constant space because we only need to keep the statistics of these microclusters. Okay, so yeah, we have all of these methods in MOA, but also we have multi-label, multi-target methods, outlier detection, so I mentioned concept breed, but also active learning, specific for streaming. We have frequent items and mining for streaming, frequent graph mining, and we have also one recommendation system. Okay, so this is what was MOA. This is MOA is an open source project that is in Java. It works only for one computer, and it's I think nowadays it's the most popular software for data stream mining. It was created in 2008, so there are many, many different methods there. But yeah, what's next after MOA? So we are presenting at KDD this year this software that is called StreamDM C++. So this is a data stream open software that we created at Huawei Noah's Ark Lab in Hong Kong. That is a streaming open source version in C++. So it has advantages as it's in C++ to be much faster than in Java, and this is because we at Huawei there was need for really, really fast algorithms. So in that case, yeah, this is what we need to have this new library that is in C++. But still, this is only for one computer, The next step, of course, for big data is to have this streaming combination of streaming and distributed system that can run inside the Hadoop ecosystem. So for this, the next step is this, what we call this project Apache Samoa. This is a project that we started at Yahoo Labs in Barcelona. So the idea is to have a system for doing stream mining, but inside the Hadoop ecosystem. So that was the main idea. So how it works, the idea is that we have all of these classifier, clustering methods, frequent pattern mining methods. We write this using the high-level API of Samoa. And then after that, we can decide where we deploy it. So we can deploy it in stream engines for Hadoop. In that case, we can deploy it in Storm, in Flink, in S4, in SAMSA. So we have different stream engines where we can apply it. The idea is that we are processing instances one by one. So in that case, it's really, really streaming. And then we can support all the stream engines that they process instances by one. And just to show you an example, so this is a vertical decision tree, vertical housing trees based on the housing tree. It's a distributed version. So in that case, it's vertical because we are going to distribute through the attributes instead of the instances. That could be horizontal partitioning. In that case, it's going to be vertical. So we are going to distribute through the attributes. So what we do here is that we have this our model that is our decision tree. So we have the stream that is arriving, and then we are going to store the statistics distributed by attributes in different nodes. And we are going to use these statistics when we need to decide if we split or not. So let me show you an example. So imagine that we have an instance that's arrived. So we're going to look at the second attribute, the green one, and the red one is the class that we want to predict. So here, the instance arrives. It arrives, goes to the leaf of the model, and then we send this information to a specific node. So we see that in that case, the second attribute goes to this node. For a new instance, again, this instance is going to arrive to the leaf, and then again, the information for the second one is going to go to the same attribute statistic node. Okay, so then the idea is that we have all the information for a specific attribute is going to be always in the same node. Okay, so this is how this vertical housing tree works. It's very important in streaming is that we don't store data in file systems. So nowadays what we do is that we use the Kappa architecture. So we use the Kappa architecture, so we use the Kafka system to store the data. The idea is that Kafka is a publishing subscribing system, and then we manage all of this information through there. So the producer applications, they publish the information into Kafka clusters, and then the consumer applications, they consume at this data, and it can be at different speeds. So this is really convenient, and it simplifies the architecture of these big data systems. So we are very thankful to all the organizations that have been supporting Samoa, Yahoo Labs, Huawei, Telefonica, also universities as Telecom, Alto, University of Waikato. And finally, we are working in another software that is specific for Spark streaming, that is in Scala. So the thing is that Spark streaming works with micro batches. It does not work with only instances. So then, in that case, Samoa cannot be applied there. So in that case, we are working in this specific software that is specific made in Scala and for Spark streaming. Okay, so just to conclude, so I tried to show you that the Internet of Things is going to be something very, very popular in the next 5 years. It's going to be many data, and there's going to be need for doing this efficient online analytics on this. And then I show you this two open source software. You have this MOA that is massive online analytics that is in Java. And it's, I think currently is the most popular software. And then we have Samoa, that is a software that is specific for distributed mining, and it's specific for the Hadoop ecosystem. So still, there are many open challenges. So we like to combine both time series and stream mining. Still, structure output, how to work with millions of classes, how to make it much easier, and how to apply it to specific applications that could be really, really interesting. So thank you very much.